many ways to comply with energy code requirements, and today we are focusing on the most significant prescriptive code compliance path changes between 2009 and 2018. Today, my colleague Kevin Frost and I will be highlighting the most significant changes to lighting and HVAC controls. So my name is Jennifer Lai, and I'm an engineer with 20 plus years of experience working in the commercial building sector. And over my career, I have worked as a design professional where I've developed some expertise in lighting and lighting controls. At Slipstream, I apply that expertise in lighting using an energy efficiency lens. Today, I will talk about the important changes to interior and exterior lighting and controls. Let's get started. So lighting power densities have of course reduced substantially, but the cost of LED fixtures is competitive today and in some instances even less expensive than their fluorescent counterparts. There have been substantial additions to energy codes regarding controls that can seem daunting to understand at first glance, but I'm going to provide an overview of those significant changes in an effort to simplify your transition from IECC 2009 to IECC 2018. To kick off the lighting controls discussion, I'd like to call your attention to a list of 11 space types where automatic lighting shutoff is required. Lighting must turn off within 20 minutes of vacancy, but a shorter auto-off in 10 minutes is reasonable with good sensor coverage. The code separately identifies requirements for on control. Automatic on to 100% is permitted in public areas like lobbies, corridors, and restrooms. Remaining spaces are, however, limited to manual on at 100% power or automatic on to 50% power or less. The designer does get to choose vacancy or occupancy on to 50% depending on the best strategy for their application. One caveat is warehouses. In warehouses, the code requires an automatic reduction of not less than 50%, but that does leave energy savings on the table, especially in a facility with long hours of operation. Full shutoff is a control strategy often well received by occupants and is most often accomplished by a sensor at each fixture. Parking garages and corridors are two space types where lighting controls are not yet required by IECC 2018, but are coming in IECC 2021. And controls in these two space types has been required by ASHRAE 90.1 since 2013. IECC 2021 will be requiring a 30% reduction within 20 minutes of vacancy in parking garages, while ASHRAE 90.1 2019 will increase the current 30% reduction to a 50% reduction. This is another application where reductions even greater than 50% within 10 minutes or less has performed well without negative feedback from occupants. Similarly, in corridors, ASHRAE 90.1 has been requiring the reduction of lighting by 50% within 20 minutes of vacancy since 2013, and IECC 2021 will add this control requirement. Current codes now require automatic daylighting controls that dim electric lighting in response to natural daylight in both side-lit and top-lit daylighting zones. These controls must dim lights to off in all but offices, classrooms, laboratories, and library reading rooms. IECC defines primary daylight zones for both side lighting and top lighting applications with diagrams to illustrate those definitions. ASHRAE further defines both primary and secondary daylight zones where these automatic daylighting controls are now required. Luminaire level lighting controls, or LED fixtures with integral daylighting and occupancy sensors, are a newer, market-ready technology. These fixtures have onboard intelligence that significantly simplify compliance with current energy code lighting control requirements, as well as the capability to implement other advanced lighting control strategies, such as task tuning via high-end trim adjustment, minimizing the risk of glare due to overlit spaces, particularly in retrofit applications. Wireless luminaire level lighting controls, or LLLCs, reduce or eliminate the need for low voltage control wiring, which can offset higher upfront fixture costs. LLLCs are also capable of integrating with other building systems, such as HVAC controls, through the sharing of occupancy data to inform HVAC control sequences. HVAC integration is an application that improves overall economics due to large HVAC savings at a low incremental cost increase. Utilities may offer incentives for the purchase and installation of LLLC products. The Design Lights Consortium, in collaboration with the Northwest Energy Efficiency Alliance, published a study in September 2020 which identifies average lighting control energy savings from these types of systems to be 49%. These savings are beyond those realized from an all-LED fixture lighting design. Moving the discussion now to exterior lighting and controls, be aware that the base site allowance and allowances for illuminated areas now vary depending on the exterior lighting zone as defined by the Energy Code. IECC and ASHRAE are consistent in this approach. Exterior controls must automatically reduce installed exterior lighting power by 30% or more between the hours of midnight and 6 a.m., or generally during non-operational building hours. A common strategy is to operate lower wattage building-mounted fixtures from dusk to dawn to meet egress and general safety and security needs, while a significant portion of the area or pole-mounted lighting dims or turns off at midnight or within an hour of building closing. This is a simple multi-zone time clock solution. An alternate solution is the use of motion controls, which reduce or turn off area lighting when no activity has been detected within 15 minutes. Some might consider this solution as a strategy that enhances security when, for example, a parking lot is uncharacteristically illuminated at 2 a.m. on a Wednesday evening. And don't forget to install or specify exterior fixtures consistent with dark sky practices. So that was a lot of information in a short amount of time, but I hope it captured the highlights. Lighting power densities that now drive the need for 100% LED installations, mandatory occupancy and/or vacancy controls, automatic daylighting controls, and controls that require the reduction of exterior lighting power during overnight hours. Next, my colleague Kevin Frost will discuss the important HVAC control changes adopted under IECC 2018. But stay tuned, we'll touch on a new prescriptive compliance path requirement that necessitates the selection of an additional efficiency package at the end of this video.
My name is Kevin Frost, and I'm an HVAC engineer with 10 plus years of experience working in the commercial building sector. Before Slipstream, I worked as a consulting engineer at an MEP design firm. At Slipstream, I applied my expertise in HVAC for field research, energy efficiency programs, and sustainability consulting. Today I'll talk about the important changes to HVAC controls in the 2018 Energy Code. There were a lot of updates made to the Energy Code regarding building mechanical systems, especially for those in commercial buildings. I can't cover all of them in this video, but I will touch on 3 updates that affect a number of buildings and will save a lot of energy: economizers, optimal start sequences, and reset sequences.
The first HVAC controls update I want to discuss are updates to the economizer requirements. Many of you already know what an economizer is, but for those of you who might not be familiar with them, economizer mode is simply using outside air to condition the building when it's more economical. There are 2 types of economizers: air side economizers and water side economizers. Here's a quick example of an air side economizer. On really hot days or really cold days, we typically only want to bring in the minimum outside air we need to. just to provide ventilation for the building. This is because cooling that air in the summer or heating it in the winter would use a lot of energy. However, since we typically supply air to the building at 55 or 60 degrees, then if it's 55 or 60 degrees outside, it's more economical to bring in that cool outside air to cool the building, instead of reconditioning the warmer room air. A water-side economizer is similar to an air-side economizer, but instead of using outside air to cool a building directly, we'll use outside air over a dry cooler to cool our chilled water. This will keep us from having to run our chiller compressors when it's really cold out. Many of the code updates apply to both types of economizers, but I'll be focusing on air-side economizers as those are more commonly used than water-side economizers. In the 2009 IECC, the code outlined when to use an economizer, but didn't have a lot more details on how to use it or how to properly implement it. The 2018 IECC provides a lot more of that detail. The 2009 code required airside economizers in Climate Zone 5A, which includes all of Nebraska, on fan systems that were greater than 54,000 BTUH, which is about 4.5 tons of cooling. In 2018, that value still applies, but the code now specifies that specifically for non-residential buildings. Residential buildings have a little bit more leeway, and an economizer is only required for fan systems that are greater than 270,000 BTUH, or about 22.5 tons. Water-side economizers are also required for large chilled water plants that are over 1.3 million BTUH and don't have systems on it that use air-side economizers. In addition, there's a new requirement that all fan cooling units not provided with economizers shall not exceed 20% of the total supply air for all units, or 300,000 BTUH, whichever is greater. This is basically saying that you can't put in a bunch of small 4-ton units, which wouldn't require economizers, to get around the requirement of having an airside economizer for larger systems. There's a number of exceptions to economizer requirements, particularly for special use cases, systems that don't operate often, supermarkets with open refrigerated cases, if you have really high efficient cooling equipment, or systems with heat recovery. The 2009 code didn't define any requirements on how to control the economizer. The 2018 IECC has several requirements for controls, and the first listed is what's called integrated economizer. In this example, let's say it's 65 degrees outside, and we want to supply air at 55 degrees. We can't cool the building with only outdoor air. However, the outside air is still cooler than the building return air, so it's actually more economical to use our cooling equipment on the outside air as opposed to the return air. This is called integrated economizer, where we're running the cooling coils with 100% outside air until it's cooler or less humid inside than outside. Here's an example of the control sequence for an economizer with integrated economizer mode. During our heating mode, we're running at minimum outside air. As it starts to warm up, we enter our free cooling mode where the outside air damper begins to open. Eventually we'll hit 100% outside air, and then we'll run an integrated economizer mode where we're at 100% outside air and we're running our mechanical cooling. And then we'll hit a certain high limit temperature where we close the outside air damper, we go to minimum outside air, and we're in mechanical cooling only. But how do you know when to switch from integrated economizer mode to only mechanical cooling? Well, there's several ways you could set up the controls. You could do it based on sensors, and there's some ways you can do it that saves more energy than others. To make it easier for designers and control technicians, the IECC 2018 outlines the high limit shutoff for economizer mode, which is when you switch from 100% outside air to minimum outside air in the summer. For Nebraska, again Climate Zone 5A, the easiest one to follow is to cut off the economizer when it's 70 degrees outside. The last economizer update I want to talk about is mandatory fault detection. Economizers can use a lot more energy than intended if they're not running properly due to poor sensor calibration or broken dampers or valves. The requirement just says that every economizer system needs to have fault detection to alert building operators to make repairs on the system. The next code update I want to go over is temperature setback requirements. The 2009 IECC required a 5-degree deadband on space thermostats. This means that for the 2.5 degrees above and below set point, the system won't make any changes to correct for space temperature. A smaller deadband would result in the system turning on and off a lot more often to try to maintain set point. The 2009 IECC also required thermostats to have a wide range to allow for off-hour setbacks to save energy when the building is unoccupied. The 2018 IECC adds a few more definitions to some of these items. The first is that you can't overlap heating and cooling set points. If you have a zone with separate heating and cooling set points, you can't set your heating set point higher than your cooling set point. The other 2018 code update is to have an optimal start sequence. This means that your HVAC system will automatically adjust the time it starts every day to warm up or cool down the building. That way, on mild mornings, the system won't run as much, but on extreme days, the system might start really early to give the building time to get to its occupied temperature set point. The last updates I want to touch on are requirements for reset sequences for multi-zone air systems. A reset sequence is a sequence that will reset a set point, higher or lower, based on another sensor input, such as outside air temperature. One example of a reset sequence is the supply air temperature reset sequence, which was required in the 2009 code. The traditional reset sequence typically resets the supply air temperature set point based on the outside air temperature. How much you reset is up to the designer or the operator, but the 2018 code requires that this must be at least 25% of the difference between the supply air temperature and the design room temperature. So, for example, if the supply air temperature is 55 degrees and the room is at 75 degrees, then the minimum adjustment is 25% of the difference, or a 5-degree reset. If you have a 5-degree reset, this just means that as it gets colder outside, you would reset your supply air temperature up 5 degrees so that you save energy when it's cold out. Another method is to reset supply air temperature based on load. For example, if there are many people crammed into a conference room for an all-day meeting, it might start to get warm in the room even though it's very cold outside. In that case, we'll want to reset the temperature back down based on the worst-case room cooling demand. This demand-based sequence is more complicated, but it can save a lot of energy. ASHRAE Guideline 36 outlines pre-written temperature reset sequences that are based on load, and these are written with input from most major control companies. You can reference these specifications when writing your control sequences. A new requirement in the 2018 code is to use a static pressure reset sequence. This is similar to a temperature reset sequence, but instead with the supply fan. In a VAV system, the fan speed is usually controlled to a static pressure set point determined by a static pressure sensor in the main duct. This ensures all VAV boxes get sufficient air. If the static pressure set point is set too high, then the fan will use a lot of energy while the VAV box dampers will try to close further to prevent too much air from overcooling the space. In the code, C403.6.9 gives a requirement for where the pressure sensor needs to be located so that the static pressure isn't too high. The 2018 code then outlines requirements to reset the static pressure based on the zone that requires the most pressure. It also requires a way to alarm if there's a rogue zone that is driving the pressure too high while all the other zones are satisfied. This is a much more complicated sequence, and again, ASHRAE Guideline 36 will have a pre-written specification for this sequence. In that sequence, VAV boxes are to send requests if they need more airflow, and the controller will trim the set point if there are no requests, and will respond quickly if requests start to come in, to make sure that there aren't any VAV boxes that are ever starved for air. Again, check ASHRAE Guideline 36 for a pre-written specification that you can quickly add to your design. The last reset sequence I want to talk about is a new requirement for ventilation reset. This is for single-duct VAV systems with DDC controls. In both the old code and the new code, you are required to have demand-controlled ventilation, or DCV, for large spaces that have a lot of occupants, spaces like cafeterias, gymnasiums, or classrooms. If you have these DCV controls installed, then the building automation system needs to automatically lower the outside air that you intake as spaces become unoccupied. This is a complicated sequence, so I again would point you towards ASHRAE Guideline 36 for guidance on specifying this sequence.
Again, there were a lot of updates to the mechanical code. We covered updates regarding when to use an economizer, how to properly control the economizer. We covered updates regarding optimal start sequence requirements. And finally, we covered reset strategies now required for HVAC air systems serving multiple zones.
Beyond the prescriptive requirements specific to lighting and HVAC controls, IECC Section C406 also requires compliance with one of 8 additional efficiency options. Most options require a system efficiency improvement beyond the basic prescriptive requirement. Design teams do have the flexibility to select the option that best fits their project. 2 options that I see most frequently selected, perhaps because of their simplicity, are either option 1 or option 2. Option 1 requires HVAC equipment efficiency to be 10% better than the prescriptive values for the type and size of each unit. Option 2 reduces the whole building lighting power density by an additional 10%. Although, if on-site renewables are being added, option 4 might be worth considering. At the start of the design process, a design team should be sure to review these 8 options to determine the best compliance path that suits their project. So we have focused today only on the most significant changes to lighting and HVAC controls. In 9 years, there have been many changes, and we do encourage you to attend other training sessions that will provide more depth on all of those changes. But thanks for watching.